1 second.
Sure. So
okay. Hi everyone. Thanks for joining today. So it's my great pleasure to introduce Wuhan Wang today as our speaker. Wuhan is a postdoc now at UCL, and before that he did his PhD at Imperial. And during his PhD, he was also an intern at Amazon. So with that, Wuhan, you can take it from here.
Okay. Thank you, Aaron, for the introduction. It's really nice to be here, and it's also really nice to be able to catch up with colleagues and mentor from my internship. So today I'm gonna present our recent works from last year.
Can you share your slides? I think
oh yeah, sure. So let me give me a sec. I need to move. So, okay, can everybody see my slides?
Yes, perfect.
Okay, cool. So I'm really excited to be here, and it's really good to catch up with old colleagues and mentor from my internship. So today I'm gonna present our work from last year's NeurIPS conference about global labels and the future learning. So yeah, I'll stop my video for now on my camera. Okay. Okay, so the focus of this talk actually is about global labels and future learning. So actually, global labels plays a very sort of a subtle but important role in the case of future learning. And in this talk, I will present a theoretical connection between the standard supervised learning and the future learning that's motivated by the roles of the dataset labels. And I will also try to propose something called a meta-label learning, which is a practical algorithm that is aimed at bringing future learning closer to real-world situations, including in the context of the AutoML, which is the theme of this seminar. So future learning is a problem of learning from limited data, right? So the figure here kind of illustrates the problem of a future classification, which is the focus of this talk. And it's also which is gather lots of research interest in the recent sort of all the recent works about meta learning and future learning. So in future classification, we have basically only a handful of samples from each individual classes that we have. And the goal that we have is basically to learn a robust models that can classify unseen sort of samples from the classes that we have seen so far. Right. And also the goal is that even if we sort of present a new task with novel classes, we should be able to also to generalize very, very well to these unseen classes and unseen samples, which are still limited. And we are trying to create a model that's good for these novel classes. So you see the training tasks on the left and the test tasks on the right. I just want to highlight a few things about sort of future learning. So conceptually, future learning is basically a task whereby you take the data set as an input, and then you pass it through some what I call a future learning, either model or service, and then the output is basically a task model, right? The model that can do well on this particular task on the novel samples. And there are three things that we are actually trying to achieve for this model. First is that we and I want to emphasize that most of these sort of desirable properties or desiderata has already been kind of implicitly or explicitly reflected in the current research. So first thing that we probably want for future learning models is that it's an automatic model creation. So given a task, the model should be automatically generated without too much of a manual sort of interventions or sort of hand tuning. And the second thing that we probably want for this case is that we want fast learning, right? So it shouldn't take too long for us to kind of to fit the data. There are only limited samples, hopefully, and then we should generate a robust model. So robust performance is also a kind of a key properties that we want here. So with all these sort of desiderata and the sort of input-output pair for the future learning, it's actually quite not difficult to see that how future learning can be kind of put into the context of AutoML. So one of the scenarios that we envision that could help in this case is that you basically have a FSL feature learning service that is wrapped around into AutoML service, right? It's something like, say, Amazon's SageMaker. And then users can submit like individual tasks, whereby they submit the task and they will be given output. Automatically, they'll be given a model output that's tailored to their task, right? So this is kind of like a scenario that in part inspire our work. So if you consider this scenario, we ask ourselves the two questions. The first thing is that how do we create a good feature learning model, right? So this is basically the question that has been addressed in lots of research papers recently in the feature learning as well as in meta learning, right? And then there's another question that we actually ask ourselves as well. So is that because this feature learning service in the production will be continue to see that more and more tasks that streaming in, from the users and all that. So the question that we automatically want to ask is that, can we actually use the task observed in the production to further refine our feature learning services so that it can actually produce so you can produce a better feature learning model and then it can serve the customers better, right? So in this particular case, what we want to emphasize is that the task here, right, in this scenario, the task is generated by different users with different goals and different, with different goals. So one particular thing is that all the tasks from all the users are independently labeled, which means that there is no coordination in how they will label the task, right? So this is a key point that I will kind of emphasize on later, which is also the theme of this talk about global labels and feature learning. Right. So just to bear in mind for now that sort of like the tasks will be independently generated by different users, and they don't really have coordinations about how they will label the tasks that they have. Of course, in this particular case, we are focusing on the classification case. There's been some ongoing work that we are trying right now to kind of like to extend the idea to regression case. But for this talk, we are focusing on the classification problem. So I will just kind of review a little bit about the background for feature learning. I mean, in this context, the meta learning is really sort of like the kind of like the dominant pipeline that people actually try to look at how to sort of like solve the feature learning. So I'm not going to go through all the sort of like different ways that we can do meta learning, but I just want to highlight a particular sort of like view that has produced the state of our results, especially in the recent works. And this one is slightly different from kind of like the traditional bi-level optimization view. It's slightly different, but not too much different. So one thing that people have noticed is that instead of doing meta learning by itself, things like MAML, prototypical nets, and all that, there's one thing that you could actually do. It's basically called feature pre-training. So in essence, you basically say you have a data set. You, instead of creating your meta learning task and all that, you just use the entire data sets that you have and then do a standard supervised classification problem or multi-class classification problem, right? So you have many like base classes data. So this is also known in the literature as feature pre-training, right? So you basically pre-train on lots of data and lots of classes, and then it's just a standard supervised classification problem. And once you got your feature extractor from this feature pre-training, then you do a little bit of what we like to call a meta fine tuning. Actually, is that the feature extractor that you have can either be, so you can either sort of like try to fine tune this feature extractor done by multi-class classification on some kind of meta learning loss, and then move on to testing. Otherwise, you could just simply use the feature extractor that's learned from the pre-training, without any modification, and then you directly move it to the testing phase. So the testing phase will be basically all your sample data will pass through this feature extractor, and you get some representation, and then you can basically, you have like a linear classifier on top of it. You can do whatever you want with it, right? You can do like a few gradient descent steps. You can use some kind of closed form solver. You can also use some kind of a bit like basically scikit-learn has lots of like linear learners, right? Like LFBGS and all that, and with regularization, you can do all sorts of things basically to learn that linear layer. And then this will be sort of like the model for you for during the meta testing phase. So this is kind of like the state of art. Basically, most of the state of art methods that we have seen so far all possesses this particular part about feature pre-training. And the important thing here is that we want to know is that in order for feature pre-training to work, it means that you must have this very, very large, like data sets with classes that's all sort of like well-defined, right? You need to have this big data set, which may not be a problem in some cases, but we'll see later that how this thing can be kind of like extended and generalized.
One quick question here.
Yes.
So what is the difference to standard fine-tuning? Well, except that you keep the feature extractor fixed.
Sorry. I think this one is so I was saying that there are basically two different modes that you can do after you have this feature pre-training. One is that if you fix so one thing you can do is that you fix the feature extractor, and then you just simply move on to the testing phase. So that's what the fixed feature extractor means here. In the other case, which is actually not shown here, so I was just so in that case, it's you have an extra phase which we call meta fine tuning, in the sense that you fine tune the feature extractor with a meta learning loss. But as you move on to the testing phase, when you try to sort of adapt your parameters for the few-shot learning task, you still keep your feature extractor fixed at that point. The only thing you will change is basically the linear layer. That's the only thing that you change at that point.
Yes.
Okay. Yeah. And thanks for the question. So we just want to highlight something. This is actually sort of like we just plot this graph of basically taking the existing results from existing papers, and then we kind of like analyze a little bit. It's like kind of like a review of the existing results. What we found is that feature pre-training actually accounted for most of the performance improvements in all the recent sort of like meta-learning papers or feature learning papers. So if you see sort of like this figure on the right, you can see that like the so in a sense that the pre-training account, so here we show sort of like two different like three different modes, right? So you have pre-training by itself, which give you a feature extractor, and we also have this thing that you have like a prototypical nets without pre-training, and you have a match net without pre-training, and then you have this extended sort of like a bar which is in a slight like a lighter shade that shows that how much of improvements is actually brought about by the pre-training. So you can see here that sort of like the pre-training by itself is doing really, really well, and it accounts for almost all the performance improvements for the few-shot learning tasks that we have seen so far. And the other sort of like things that we notice here is that pre-training is actually a very ubiquitous thing that you can apply that to almost any sort of like few-shot learning methods that you have seen in the literature. And also they have been used extensively to achieve like state-of-the-art results. So the question that we want to ask ourselves is basically twofold, right? One question is that why is pre-training like really, really good for generalization performance? And the other question I want to ask is that what if we don't have global labels, in a sense that I discussed about that in order for you to do this pre-training, you must have a really, really large data set, with all the labels that's kind of like, nicely like labeled for you. So this actually doesn't really fit into the scenario I mentioned earlier about the AutoML, about refining the service online, right? Because when the task becomes independently labeled by different users, then you don't have this nice coordination where all the labels are actually sort of like consistent, right? You don't really have that guarantee anymore. So you don't really have global labels. So in that case, can we still do something to sort of like to, if we don't have global labels, can we still do something to sort of like to improve the performance of a few-shot learning? So this is where we're coming from. And this is also where the context of the AutoML, at least this is sort of a realistic scenario that partly inspire, this work.
I have one.
Yes.
So I mean, you always have something to pre-train on, right? I mean, but what you're meaning that is you're pre-training on a set of classes that includes stuff that you want to look at later on, in some sense, right? I mean, so images, you always have image data sets. You can pre-train on them. It doesn't. So, but I'm just trying to understand what you mean with that you don't have that. I mean, unless you have a very unusual input kind of stuff.
So that's why I was motivating it with the scenario that I mentioned earlier, in the sense that yes, for learning like an initial model, you always have like a big data set that you can curate, right? But in a sense that once the service goes online, then you continue to receive sort of like tasks from users and all that stuff. If you can make use of that data to refine your service and to refine the model, then you lose the ability of this global labels. right? Because the task that's been supplied by the users, they are independently labeled and they don't have any coordination or consistency at that point.
So if you want to use this data as well, then you have the usual problem that people maybe call continual learning or lifelong learning or something. So that's what you mean, right?
Yes, yes.
Okay, good. Yeah.
Okay. Yeah, thanks for the clarification. I think I probably wasn't very clear on that. This is a good question that kind of clarifies it. So we are also trying to address basically this scenario where, like, in some sense, similar to continual learning or lifelong learning, in the sense that the data continually comes in, stream in, and then you don't really have this nice property about global labels anymore. Then what can you do with it, right? So this is basically the question we're asking. So the theoretical connection that we were able to prove in this paper is that basically we can consider, the gist of it is that the pre-training can be actually considered as a conditional method learning. So the proposition that we prove informally basically says that the pre-training actually is an upper bound to a conditional method learning problem where the task classifier W bracket Y, which is a special function that we have, simply maps like global labels to task weights. And then you have this theta, you have this phi theta, which is the feature extractor. So what I mean by that is actually quite intuitively explained by this figure, in the sense that if you imagine that you have lots and lots of classes to train a multi-class classification problem, then let's think that hypothetically, if you want to convert this model into a few shot learning model, and provided at this point that if you assume that you actually have access to what classes you are going to classify in this few-shot classifier, right? We can use a very special task classifier in the sense that we can basically just take out the rows here that corresponds to basically the classes that you want to classify and mask out all the other sort of like columns from the last linear layer. And then this will give you a few-shot classifier automatically, without even doing any kind of training on this data, on the new data that you will see, right? You can see all the novel samples for the same classes they have trained before, and you don't have to fine tune it at all. The only thing that you probably need to do, if you know the classes where these samples are generated from, then you just take the rows, basically take the rows from the last layer that corresponds to the classes. And then this will give you a few-shot classifier. Okay, so this is a kind of a simple concept. And then more formally, mathematically, what we can prove is that this, basically the pre-training, the cross entropy loss, that is actually upper bounds basically the conditional meta learning loss, whereby you have X and Y, which is a task that you have, a few-shot learning task you have, with X being the input and Y being the output. Assume in this case that you actually know the global labels. In this case, there's no need for you to utilize the data X to train for how to classify this data at all. The only thing that you need to do is basically say that if I learn something global, which is the W, which is the last layer of your multi-class classification problem, you can just take the corresponding rows from that particular matrix, and then this will give you a very effective task classifier. So in this sense, the pre-training actually upper bounds the loss on the left, and the loss on the left it's called a conditional meta learning loss, precisely for the reason that we are not really only using the data, which is X, to train our classifier, but we're using so-called the side information, which is from the label itself, to generate the classifier, in this case, the linear classifier, holding the feature extractor constant in this case, right? So this is what we meant by conditional meta learning, in a sense that in addition to the data that you have, you also have this a little bit of a side information, which is what these labels are. And in this particular case, these labels must be global labels, in the sense that across all the tasks that you have seen so far, there's a consistency about how the labels are being given. So global labels provides a bit more extra information compared to the local ones that you're seeing normally in a meta learning task, in a few-shot learning task. We'll go through this in a bit more details later, more visually. So basically, this gives you a bit of extra information. So in the sense that pre-training actually provides extra information to solve this meta learning problem, to solve meta learning or future learning problem, in the sense that it provides you something that's global. It provides you information about global labels. And this is sort of like extra information that helps you to solve this feature extractor. And this feature extractor will be more sort of like powerful and more robust. And this can actually be linked to another paper from the group that where I did my where I was doing my postdoc. Basically, they proved that conditional meta learning actually incurs a lower excess risks and improve generalization performance as soon as you provide additional information to this meta learning problem. In this case, the additional information is provided as in the form of a global labels. And this is actually what you are doing when you are doing the pre-training. And we can show that this is the upper bound to the conditional meta learning loss, which means that as soon as you are doing pre-training, you are implicitly optimizing for conditional meta learning loss as well. So that's why sort of like there's this connection between multi-class classification as well as meta learning in this case. And that's also the reason why pre-training is very, very effective in constructing basically a feature extractor that is actually more robust than the one that you can obtain by simply training on the meta learning loss on future learning. Okay, so this is sort of like the gist of it. So we now understand a little bit more about sort of like why sort of like you know, the future pre-training is so advantageous for meta learning, and we already seen previously from our review from other papers as well, in a sense that like why sort of like you know, like future pre-training is producing the best results, right? So now we move on a little bit to the second question that we have, in the sense that what if we actually don't have the global labels? You know, then what can we do about it? So basically in a sense that like most of the papers, they will always say that this pre-trained data sets is constructed by grouping the samples with the same global labels, right? So you know, like you basically have so you group the labels and you generate this pre-trained data sets, right? They still start from this notion that you have like tasks rather than data sets. Well, of course, there's also the argument that to say that we always have image data out there, and we do have like a large sort of a database for us to pre-train the things. So the grouping becomes inapplicable, right, when the tasks are independently annotated with the local labels. This I already kind of elaborated a little bit about. So imagine that you only have local labels that's independently labeled by different users and all that stuff. So all you can see is basically local labels like 1, 2, and 3. So in this case, if you just kind of like naively merge the tasks based on the local labels, this is gonna be like, this is not gonna work. And then you cannot really recreate this pre-training data sets. And then you cannot really do this pre-training as a, even though it's more advantageous than just simply using meta learning to solve a future learning problem, but you cannot really do that. So this is basically the thing. But we can actually leverage something from the local labels. The local labels actually basically give us 2 pieces of a task constraints. And for every task that you have, it gives you 2 pieces of constraints that we can utilize and can exploit later. So the first piece of the constraint that it says is very simple. It basically says that if all the labels share the same local label within the same class, then assume that there are some global clusters that you want to assign them to, then these samples must be assigned to the same global cluster, right? So you can see here that, so for the first task, all the red ones should be assigned to the same, you know, should be assigned to global cluster 1 because they share the same global label, and share the same local label. And then the you know, the cats, which is a local label 3, and they should be assigned to, say, hypothetically a global cluster 2 because they share the same label within this task, right? So this is the first piece of constraint that we want to respect. And the second piece of constraint that we want to respect is basically that if within the same task, samples are assigned different labels, then they really must not be assigned to the same global cluster. So this is also a very direct sort of like, you know, constraint that we can see. So in the sense that if we assign the flowers in task B to, say, global cluster N, then we must not assign dogs in task B to the same global cluster, because this will violate the local task constraint that, you know, they cannot be assigned to the same global cluster, right? Assuming that we have some global clusters that we care about. So these are basically the 2 pieces of a task constraint that we actually have. So how do we make use of these task constraints?
Can I ask a quick question?
Yes.
So in task B, why is flower not part of global cluster 1?
So this is basically to reflect the reality that because you don't really know they are flowers. Remember, as I mentioned, that you only, in this case, you only access the local labels, which says that this is just a local label too. So there is a chance that you will assign it to another global cluster, because I will like the global clusters may not be perfect. They could be good, but they may not be perfect, in the sense that there is the possibility that you assign it to another cluster. Even though ideally we'll probably want to if we know that they are all flowers, then we want to assign them to the same global cluster 1. That's all. Does that answer your question?
Yeah, got it. Thanks.
Okay, cool. Thank you. So yeah, so the second piece of constraint, as I mentioned, is that basically if they don't share a local label within a same task, then they shouldn't be assigned to the same global cluster. So these are the 2 pieces of constraints that we want to exploit. So what we found is that there's something that we can do to actually recover these sort of global labels or infer global clusters. And then the procedure for this is actually fairly sort of straightforward. The first thing that we want to do is that we basically apply any standard meta learning task that we have to learn some initial feature extractor, like we call it phi0, right? So you can learn it with any methods that you like. You can learn it with, like, say, prototypical nets. You can learn it with Memo. We prefer to use basically R2D2 because of its speed and because they has a closed form solution, and it's a faster to learn, computationally more efficient and more stable to learn during the practice, right? But you can use anything you want. You can use Memo, you can use ProtoNet, whatever you want to learn this initial feature extractor. And then what we do is actually we want to cluster all the task samples using this phi0 as a similarity measure, while at the same time we want to enforce all the task constraints that we actually have. So we have just talked about in the previous slides. So the clustering is basically a modified k-mean procedure, in the sense that we just cluster with basically also enforcing the constraint. There's nothing too much too weird about it, right? So, and also after we do the clustering, we have some pruning to get rid of the small clusters, and then we redo the clustering procedure again, also enforcing the task constraints. So we can do this repeat this procedure for a few iterations, and then we'll stabilize to basically a stable number of global clusters, and then we will stop, and then we will return all these clusters that we have inferred as the inferred global labels. And then right now, since we have generated this new sets of inferred global labels, we can apply the pre-training that we talk about, which is basically just multi-class classification with the inferred labels, right? And then we can generate that. We can sort of follow the same procedure that I described earlier, in the sense that we do the pre-training to generate, a feature extractor, and then we can do some kind of meta fine-tuning and all that, and then we move on to the meta testing stage, right? So this is so basically the process of the meta label learning. So
can I ask the question?
Yeah. Yes.
So here, you're finding these global labels and doing multi-class learning. So what if I were to do multitask learning? So I have these tasks which with possibly shared labels. And if I do this multitask learning, do you think the model will itself figure out these clusters?
Multitask learning, in the sense that they have like different prediction head?
Yes.
Yeah, that's a good question. We haven't tried it yet, but my guess would be that it probably would work too. I think in that sense, it's actually fairly similar to say basically like R2D2, because R2D2 basically generates the linear classifier, which is the last layer on the fly, through a closed form solution. So in the sense that even though they don't store they don't store the sort of like the weights for the last layer, but it's implicitly there. I think the only sort of issue here is that for the formulation of few-shot learning in the context of meta learning, there's always this sort of like you have like a support set as well as a query set. So in the sense that you try to generate the last layer, or you train your last layer based on the support set, and then your gradient actually comes from the query set. that you have. So if you formulate it as a multitask learning problem, then there's a little bit of a tension in the sense that like, how do you kind of like juggle these like two small sort of like pieces within a same task together? I think that will be sort of like a slightly technical issue, but my hunch is that it will probably still be able to work. I mean, the idea here is basically that you need to have some feature extractor that provides some kind of a similarity measure. So in some papers, then they even discuss about saying that, you know, like unsupervised learning will be able to provide you with a similarity measure. Of course, we haven't tested how well that one could be used to sort of like do the clustering that we are proposing here afterwards. But I mean, the idea is basically that. And also in a sense that since we already have some kind of local labels there, so unsupervised learning seems to be like, you know, like way out of the, you know, it's not necessary to discard all the local labels that we have, right? So in a sense that like we can just use some kind of standard meta learning problem to extract the feature extractor.
So one I
Yes.
just don't really see why this could be better than, you know, it seems like you're doing the same thing twice, like Protonet, and then at the end you do global labels, and then you do Protonet again. And I just fail to see why that would do anything better than just Protonet. I thought that, you know, okay, Protonet, you can improve on it by using something pre-trained, but that's simply using new information. But here you're kind of, I don't know, I mean, you see what I mean? I mean, there's no new information coming in here, right? I mean, this Protonet is just making labels up or groupings up. And then you say, oh, these are correct, so let me fix them and pre-train, and then you use this Protonet again, right? Why? I don't know. I just don't really get what's the, you know, well, I mean, why wouldn't this be doing things at random more or less, right? Or not better than Protonet?
So in a sense that I think that is your problem more concerned with, say, the meta fine tuning part?
Well, I mean, so I understand that if you want to do something like meta learning and you use a pre-trained model and you start from there, I understand why that is better than not doing it, right? That was your figure in a few slides ago. Yeah. Because the pre-trained model has a lot of extra information. It's been trained on, you know, it's been trained to, you know, how do you discriminate images, right? Yeah. But here you don't have that, right? I mean, you just come up with that information with the method that you want to enhance by some extra information. And so I mean, I know that people do that, right? The self-training. And so you kind of, I mean, you know, it sounds a bit like you train a model, you create labels from it, then you fit the model to the labels again. It's like, you expect this to be better than before. I just don't really get where the new constraints coming in that gives you some benefit by doing this 2 times.
Okay. Yeah. Thank you for this question. So I will show it in the experiment results later. So the quick answer to the question is that what's really important here is that we are enforcing the task constraints. This is what makes all the difference.
Yeah, but I mean, I could do that by just making up new labels for every task. I just, you know, say tasks _ label, right? So I have a tons of, I mean, obviously then you would say, oh, that's too many, right? So let's make them smaller groupings. And now I'm just wondering, what's the force that brings 2 of these? You know, think about as many groupings as you have total different labels, right? So every task has labels. So that would be totally trivially, you know, respecting all your constraints, but obviously that's not what you want, right? So now what's the thing that brings the right stuff together?
Yeah, so I mean, I think in a sense that like we also try sort of like to have like really lots and lots of classes, and as you have correctly predicted, the performance is a lot worse. So in a sense that like our hypothesis is that basically you need to bring the number of sort of like the you need to bring the number of clusters to a reasonable level. But of course we are not able to you know, there is nothing in our proof to suggest that what is a sort of like a reasonable level of the what's the reasonable level of the classes. All we can say that empirically is that if your basically the number of classes is you know, like because for the experiments that we have done so far, we do have some kind of ground truth about, you know, like how many labels that we actually have, right? So in a sense that if we don't deviate too much, you know, like in a sense that like 30-40%, still quite robust in a sense that we don't deviate too much from the actual number of labels that we should have, then this procedure actually works out really, really well.
Okay, yeah, fine. Move on. I missed something.
So this is sort of like some of the results that we have seen. We have seen here. So in the sense that the so we only in this case we're testing on mini ImageNet and tier ImageNet, and the constraint that we have here is that we are only giving local labels to all the tasks that we have. And then, of course, in our case, we are trying to use the infer labels. So nobody has like pre-training, right? In this case, nobody can do pre-training. It's except for our method in the sense that we infer the labels and then we do the pre-training afterwards. But we are using the infer labels, right? So this is for the fair comparison in some sense. And we have more results in the paper. So you can clearly see that our methods, by trying to infer these global labels, we can do a lot better than, you know, all the competitors' methods that we have seen here, in a sense that like we have like a significant sort of improvements in terms of performance that we can get, just because that we are trying to infer the global labels and then we exploit sort of the advantages of the pre-training, and then we generate a much more robust you know, feature representation, and this allows us to get a performance that's much better than the competitors. So we also sort of like try to understand a little bit sort of like how well can we generate the, you know, like these how well can we really infer these clusters, assuming that we have some kind of like you know, like global truth, because for the data sets that we are testing on, we do actually know what's the global truth, right? So you can see here that for mini ImageNet, the problem is actually fairly small because it only has like, you know, like about 64 classes. The accuracy of the inference in terms of clustering based on the initial you know, the feature representation that we have is actually really good as long as we enforce the task constraint. So we can actually get to about 99.9% accuracy in terms of you know, like clustering in terms of like clustering the samples into the right global clusters. So one caveat I want to talk about here is that in the sense that the things that Matthias kind of mentioned can come up in the sense that we can have, like, say, two global clusters that's serving the same class, in the sense that this ground truth, like, or a single class, right? A ground truth class can be split into like two subsets, and each one of the subsets will contain like kind of a half of the samples from there. This can possibly happen. Exactly for the reason that because we try not to assume that how many sort of like infer global labels that we should have. In our algorithm, the infer labels is actually done by you know, the number of global clusters that we infer is actually sort of like you know, generated by a pruning process, in a sense that we do the clustering in one round, and then we prune sort of like the smallest clusters based on some criteria, and then we redo the sort of like assignment again, and then after a few runs, we see that empirically the number of clusters will stabilize at a level, and then that's when we terminate the process of clustering, and then it will generate, like, basically that's how the number of like inferred global clusters that we have. So in a sense that we may infer like 65, 67 classes instead of 64, that's okay. But the key thing here is that even for the extra free classes, they are basically most likely a subset of a ground truth class, in a sense that the samples within that particular you know, like inferred cluster, they are still belongs to the same class. It's just that they are subsets of it. So in a sense that let's say for if you have a class dogs, maybe the cluster that we infer will have, say, you know, like Huskies versus, say, Labrador, right? And then in the pre-training, there will be a split between the cluster of you know, Labrador and Husky, but they still sort of all belong to the overall class of a dog. So and also for the tier ImageNet, we can achieve sort of like this accuracy of a 96.4% in terms of like how well we can classify it. And what we have found is that enforcing task constraint is really critical for the clustering performance. This is basically shown from the next slide. So in a sense that we are using a modified version of a k-mean while respecting the task constraint. And so it's a very simple, straightforward question for us to ask is that can we just sort of like use k-mean and we just use the initial feature representation learned by the meta learning, right, or feature learning, without sort of like enforcing the class constraint. You can see that this actually works pretty well for mini ImageNet because the number of classes are quite small and they are actually quite distinct in terms of what classes they have. But this performs really, really horribly if you move on to the tier ImageNet. Sorry, if you do standard k-mean as a clustering mechanism, you only get about 28.2% clustering accuracy. And if you train on these imaginary labels based on this k-mean alone, then the performance is actually, it's more or less in line with just sort of like standard feature learning. There's nothing too much about it. But if you actually respect the task constraint, you can go all the way up to about 96% in terms of labeling cost accuracy, and this will have a huge impact in terms of how you do the in terms of the feature extractor that you extract. And this will give you like a much better boost in terms of the final sort of like feature learning performance. So this also sort of like give us a little bit of I wouldn't say this algorithm is sort of like the whole picture, but this at least give us a way sort of like to address the question that we asked earlier about, say that in a sense of a continued learning or sort of online learning, how this algorithm can be used. So our vision is something like that. You continue to see tasks that come in, and then you basically store them, right? And then you can basically use this clustering mechanism once in a while to assign sort of like infer global labels to all the tasks that you have seen so far, right? That's been independently labeled. They don't share global labels. And then you can essentially retrain your few-shot service using all these imaginary labels. And then if it's similar to what we have observed here, then you can reasonably expect that the few-shot learning, sort of like the model that you redeploy, after training on all these new tasks that you have seen, will be better than the ones that you deploy initially at the beginning. So this is sort of like the way we kind of see that how this algorithm could be potentially useful in practice. So in summary, so we kind of like show that pre-training indirectly induces a conditional meta learning problem, which also explains theoretically why sort of like pre-training is really necessary and good for the few-shot learning problem. And we also sort of like, it's known to us that, like conditional meta learning is known to improve generalization. And this is something that's a bit more general in the sense that if you have additional sort of like information to give it to the meta learning, it's probably a good idea to give it to it. And then you will generate like more robust models. And we also sort of argue why global labels may not be available at sometimes, and we show that they can be inferred, through a clustering methods that respect the task constraint that we have. And the infer labels are applicable with lots of methods that we already have, in the sense that the algorithm that we proposed was actually fairly generic, in the sense that you can use a lot of different methods to generate the initial embedding or the initial like feature extractor, and then you use that as a similarity measure for the clustering. After that, you can just sort of like repeat the process and then improve, refine the models that you have. Yeah, so that's all I have. So the papers is called The Role of Global Labels in Feature Classification and How to Infer Them, and this is the link to it. And if you have any further questions, I'll be happy to answer them.